right, welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Jiaoyang Li, who is an assistant professor at the Robotics Institute of the Carnegie Mellon University School of Computer Science. So something about her, she received her PhD in CS from the University of Southern California back in 2022. Her research interests are in the coordination of large robot teams, as you can see from the title of today's talk. As you have seen, she has won a number of awards and she has a number of ongoing collaborations. Also, something that's cool that started recently is this League of Robot Runners, sponsored by Amazon. In her PhD dissertation, she also received awards from UHC itself. So we are very excited for today's talk because she's going to talk about intelligent planning for large-scale multi-agent coordination. And without further ado, I give you the stage, Jiaoyang.
Thank you for your nice introduction. Hi, everyone. So yeah, I'm Jiaoyang, and I'm currently at the Robotics Institute at Carnegie Mellon University. So I joined the institute like 2 years ago. Before that, I was a PhD at USC. So in today's talk, I will actually cover material, like most material like that we done here at CMU since I joined here, but also I will cover some materials that I did in my PhD, especially the first part of the talk. Okay, so let's get started. So nowadays, like robots become more and more important and more common in today's warehouses. Like here, I gave you like several examples of different warehouse setup, and like as you can see here, right, like for different type of warehouses, people design different like robot systems to help the warehouse to move like packages or inventory pods around inside the warehouse. So although like the design are very different, in many cases, they can have very large team of robots. So I put some numbers here to show like for those like leading companies, they can have sometimes thousands of robots. And even for smaller like companies, they can still have a few hundred robots inside their warehouse. So although here we have different designs and different warehouse systems, for all these kind of problems, they have one key underlying same challenge they need to tackle. And in the academy, we call it multi-agent path funding, or MAPAF for short. So MPF is a short name, and I would call it MAPAF. And so this is an abstract problem of the actual navigation problem that the robots face. In this problem, like this is a video I always use. We are given a map, which is a graph that the robot navigates on. And we are given the start and go locations of the robots. Our task is to plan collision-free paths for the robots that minimize their travel times, or maybe some other objectives that you are interested in. So this is a very simple definition. But this is a challenge problem in practice. So here I show some simulations. It may not work that well, like when I stream it through Zoom, but I hope you can get the rough idea from the simulators. What we see here is a simulation that simulates 800 robots in a sortation center warehouse. And this simulation actually I did during my PhD internship at Amazon Robotics. So what we have is that on the left is a simulator that uses relatively traditional or widely used old techniques in the industry, where every robot plans its own path. Like it's either a shortest path or maybe a path that minimizes the expected travel time. And then they resolve collisions by some local traffic rules. Just like today's road network, right? You have traffic signals. For these robots, they also have some local rules, like who should stop, who should go first. And that's like a very popular method for coordinate robots in the warehouse. As you can see here, it's a method that works. It's a simple method, but it can cause a lot of traffic congestion when we have many robots. Just like today's road network, right? You see a lot of congestion when you have too many cars on the road. And then what we see on the right-hand side is exactly the same simulator. The only difference is that we use a more clever or more intelligent planning method to coordinate the robots. And in this case, like the robots can make better decisions about which route it to take, and also better decisions about how they're going to resolve collisions between them. And as a result, we can move all the robots very smoothly, almost no congestion. And therefore, in the end, when we look at the throughput of the system, we can see a big improvement. So what we see in this figure is that the x-axis is the number of robots, y-axis is throughput, basically how many packages or how many goal locations the robot can reach. So when the number is small, there's no big difference between the naive method and the more intelligent method. But when you have more and more robots, the naive method suffer from bad traffic congestion, while a good planning algorithm can keep increasing the throughput almost linearly and eventually hit a higher throughput and a higher scalability. And so warehouse is just one of the examples where we need coordination of large team robots. But I believe that in the near future, we'll see more and more such applications with the advancement of robotic techniques. So here I gave some examples, right, in manufacturing or for drones, or even in the future for autonomous vehicles. There are so many cases that where we will have large team of robots in a shared environment, and we need to coordinate them more efficiently to perform either like their individual tasks or perform some joint tasks that a single robot cannot do alone. And therefore, with this motivation, so we studied the following several research questions behind this problem. The first one is the motivation path finding, the backup problem itself, basically how we are going to plan good paths for a very large team of agents. So we tackle good solutions, and in the meantime, we want the algorithm to be as scalable as possible. I will then talk about how we combine this with the execution part, with the goal that during planning, we'll always build a simplified model of the robots, and then we will use the good combination with execution with the controller so that we can make the whole framework more robust in terms of like handling uncertainties and handling different types of robot dynamics. I will then give a relatively simple like introduction about how we further combine this technique with task planning, right? We need to first figure out, given the task, we need to figure out where the goal locations of robots are and then how they are going to perform those tasks. And last but not least, I will talk about some very recent work we did in our lab where we look at how we design good environments for these robots to navigate so that we can improve the performance of the entire system. Okay, let's look at the first part, path planning part. So to begin with, I will give you a formal definition of what map path is. So in map path, we are given an unweighted graph. And in today's talk, I will just use a 4-neighbor grid to represent the graph for simplicity. And then we are given a set of agents. Each agent has a start location and a goal location. And we'll assume that at every time step, an agent can either move to a neighboring location, like in the grid case, it's up, down, left, and right, or it can wait at its current location. So there are two types of actions. And we define two types of collisions. So a vertex collision happens when two robots try to move to the same location at the same time step. And an edge collision happens when two robots or two agents try to swap their location or go through the same edge, right? If you think about as a graph at the same time step. And with all these assumptions, then our goal is to find collision-free paths for all the agents. And in the meantime, we want to minimize the sum of their path costs, which usually defined as a travel time, like a sum of travel times of these agents. So for example, for this particular map instance, here is an animation of our optimal solution where agent 2 wait one step here, right? And then to avoid collisions, and then they can both move to their goal locations. So just put some like implicit assumption, like explicit. So for now, we'll assume this is a deterministic world, and we know everything in advance. And also we'll assume this is a centralized system. So in the later part, when we talk about controller, we will relax some of the constraints here, right? We will consider robot dynamics there, we will introduce uncertainty there. But in the first part, we do the pathfinding, we will make these assumptions to make our problem easy enough so that we can solve large team of agents. But even with these simplifying assumptions, this is still a very, very challenging problem in terms of computational complexity. So people show that it is an NP-hard problem solved optimally, and actually in some cases, it's also NP-hard to solve boundary suboptimally. But still, since with all those like motivating examples, right, we do care about solution qualities. And for me, as like a planning person, when I see a new problem, I still want to start with an optimal algorithm to understand what's the key challenge behind the problem And from there, we can develop like speed up techniques or extend the framework to like suboptimal algorithms. So therefore, let's start with the optimal algorithm. If we want to solve this like pathfinding problem, map problem optimally, what's the first choice? So like if you're familiar with like search or planning algorithm, the first algorithm you have in mind is probably A star, right? Which is a very popular, widely used optimal algorithm for pathfinding. Traditional A star is for plan paths for single agents, but here we have multiple agents, and therefore we will apply A star in the what we call joint state space of all the agents. Right? What I mean here is that to begin with, right, you will generate your root A star node, where your node consists of both locations of the agents. So in this case, A2 is the start location of agent 1, B1 is the start location of agent 2. And then you generate child node, which are all possible locations of the agents at time step 1. Right? Then you compute the J and F and J and H, and then find the node with smallest F value, for example, this node. And then you will enumerate all possible locations at time step 2 that the robot can reach from this location, right? And then you repeat this. By the time you find the node that corresponds to the target locations of the agents, right? That's when you will stop, you will backtrack, and then you are able to get a set of collision-free paths. And because of A-star search, you can easily prove that the solution you get here is an optimal solution, a solution that minimizes the travel time of the agents. So great, we already have a first algorithm that can solve the problem optimally. Let's look at how it performs empirically. So the first part of the talk, I will use this particular benchmark map to show compare the performance of different algorithms. Here, the x-axis is number of agents, y-axis is success rate. So what we mean by success rate here is that we will give a runtime limit to the planner, like 1 minute in this case. And success rate means the percentage of instance that the solver can solve within 1 minute. And what we see here for A star is that it's an optimal algorithm. For 3 agents, great, it solves all instances. For 5 agents, it solves like 80 something, 90% of instance. But when you have 6 agents, its success rate drops to 0, which means theoretically A star is optimal and complete, but unfortunately, this algorithm is not scalable at all. And this is not surprising because you can imagine, right, the joint state space grows exponentially in the number of agents. So it's not surprising that A star cannot scale well. And this is like a widely known problem in the community. And therefore, about like 10 years ago, people actually proposed a much, much better algorithm, which is called conflict-based search, or for short called CBS. So CBS searches what I call it a collision resolution space instead of a joint state space. And that's the key idea for speed up the entire process. So let me give you an example how the algorithm works. So we take this example, and the first step CBS does is to plan a shortest path for every agent, ignoring collisions. So just run a shortest path find like a normal A star algorithm for an individual single agent for all agents, and then you check for collisions. So in this case, the 2 agents collide at location B2 at time 1. And when you see a collision, what you do is that you will try to resolve this collision by saying one of the agents has to avoid this colliding location at this colliding time step. So in this case, it's either agent 1 or agent 2 cannot be at location B2 at time 1. And then therefore you will make a copy, actually make 2 copies of the original problem and treat them as like a child node of the original problem. And then in each child node, you will add 1 new constraint, right? It's either agent 2 or agent 1 cannot be at the colliding location at colliding time step. And then each child node, since you get 1 new constraint on a particular agent, you will replan the path for that particular agent. So in this case, you will get a new path for agent 2 here and a new path for agent 1 here. And then you just repeat the process by checking for collisions again. And if there are collisions, you branching again. So you can see here, this gives you a binary search tree on the collisions, in the collisions resolution space, right? And CBS perform backward search on this binary tree, where the cost of each node is just like the sum of the path cost of the current path in the node. And then you can easily prove that when CBS finds a collision-free node, then the solution there is a collision-free solution, and it is an optimal solution because we perform backward search on the binary tree. And therefore, so A star, CBS actually has the same theoretical guarantee as A star. And empirically, as you can see here, it performs way better than A star. And the reason here is that every time we CBS plan path, it'll always plan path in the single agent space. It just we plan path many times because of new constraints, but in most cases, it plan path in single agent space, and therefore it scales much better. So here I have two lines here. The slight difference between them is that the green line here make a better decision about collision selection. So namely, if you say multiple collisions in one CBS node, the green line makes a good decision about which collision will actually resolve first. But overall, so now you can see we can scale up to like 150 agents, which is very, very large, right? We are talking about optimal solutions. However, if you look at here, with only 4 agents, the success rate of CBS is not 100%, which means in some cases, CBS can solve 150 agents within 1 minute. And in some cases, with only 4 agents, CBS fails to find an optimal solution within 1 minute. So there must be something like very, very simple, but CBS is very, very struggle with and hard to solve it, right? So therefore, in order to make this kind of algorithm more practical, like more robust or more stable in terms of performance, we want to figure out the reason why this happens and develop technique to address it. So it turns out that this particular failure is caused by a phenomenon what we call collision symmetries. So here I will give you an example. As you can see here, I plot the same instance we have already seen 4 times. And then in each figure here, I draw different shortest paths for the agents. So as you can see, for each agent, there are multiple shortest paths to its goal location. But if you try this shortest path, you will soon realize that all combinations of these shortest paths collide somewhere inside this yellow region. They all collide with each other. And therefore, actually, if you want to find collision-free paths, you have to ask one of the agents to wait for one time step. But this is a bad example for CBS because according to CBS logic, CBS has to try many combinations of the shortest path because its low level is always a single agent path finding. It always plans the shortest path. So it has to try many combinations of the shortest path before it realizes that, okay, actually one of the agents has to increase its cost. So this will be the eventual CBS tree that we need to solve this particular instance, where we actually expand 5 nodes and generate 11 nodes in total. And this becomes even worse if we increase the size of the yellow region, like put the start and goals further away from each other, but still have only 2 agents. So this figure shows that when we increase the size of this yellow region, the number of nodes CBS expanded grows exponentially. So with the size of only 9 by 9, which is still a relatively small size, CBS has to expand 600,000 nodes to resolve collisions between just 2 agents. And actually, that's the reason why like it performs very bad when you have very few agents in some cases. And unfortunately, like the symmetry I showed just now is just one of the many, many symmetries that exist in the MapPath problem. So I give you an example of this rectangle symmetry, which is actually a symmetry that's particularly popular when we use a grid graph. But there are also many other symmetries that I show them grid graph here, but they can actually also occur in the general graph, like root graph or whatever other graph you are using. And therefore, so our like goal here is that to develop efficient techniques that we can discover these symmetries, and then develop good techniques that we can resolve them in a more efficient way instead of letting CBS do exhaustively enumerating all possible combinations. And the idea we use here is inspired by some constraint programming like techniques called symmetry breaking constraints. So the idea here is that whenever you find a collision, instead of just focusing on that particular collision and add a single constraint to resolve that particular collision, we will add a set of constraints to each CBS node with the goal that we want to resolve all the symmetry collisions in a single branching step. But there are also constraints here because you cannot add like infinite number of constraints arbitrarily to your channel because we still want to preserve the completeness and optimality of CBS. And so there's this trade-off, right? You cannot make a constraint set too large, but you also don't want to make it too small because there's this incompleteness issue or versus like the inefficiency issue. So I won't go to the detail about how we design the constraints, but in the past, like I did some paper here, so we actually developed methods that both can design constraints manually and also can design constraints automatically. So here I'll just give you one example about how the constraints look like, what I mean by these constraints. This is the old like CBS tree we say, right? Resolve constraint with a single, resolve collisions with a single constraint. If we use symmetry breaking constraints, this will be the constraint we are going to use. So what happens here is that for the left child node, we'll say agent 2 cannot be at location B3 at time 2, and it cannot be at location C3 at time 3. So you can say with these two constraints, it blocks all shortest paths for agent 2 to reach its goal location. And therefore, when we reply agent 2, it has to wait for one time step and then move. And because of this wait action, there's no collision in this node. And the real child node is very similar. So with this, you can see that this pair of constraints can resolve the collision symmetry in a single branch step. And in theory, we can prove that this pair of constraints still preserve the completeness and optimality of the algorithm. So when we have this technique, after we combine it with the previous CBX framework, this will be our new algorithm. So now we can scale up to like 210 agents, which is slightly larger than previous 150 agents, right? But to me, the more important improvement is here, where the previous like 100 success rate number is only 3 agents. Now it becomes 60 agents. So algorithm now becomes much, much more stable. And of course, there are many other things you can do for the on top of the CBX algorithm. So in the past, we also studied heuristics. So as mentioned, the high-level search this binary tree in a best-first search manner. If we turn the best-first search into an A-star by introducing some divisible heuristics, we can further improve the scalability. And then because like the divisible heuristic we divide by hand, so if we use some learning techniques to learn some heuristic and combine with the divisible heuristic, and in the meantime, if we give some relax on the solution quality, right? So this group brown line particularly relax the solution quality by 2%. And in this case, we can have a much like big like boost in terms of scalability to like about 1,000 agents. And then furthermore, if you want to you are willing to relax like this theoretical guarantee in terms of solution quality, we can use some local search method to further improve the performance. Well, eventually this pink line can scale to a few thousand agents, and empirically its solution is still not that bad, still relatively close to optimal. So with here, we can say like we provide a spectrum of algorithm to solve this particular multi-agent pathfinding algorithm. And therefore, so if you have your particular domain and problem, just take your domain, take your map and run the algorithm, you can get a spectrum. And based on how scalable you want your algorithm to be, you can select the algorithm accordingly. So that's very nice. But on the other hand, this is not like the end of the pipeline, right? Because we are not solving the multi-robot coordination problem yet. Everything we talk about here is some agents moving on a discrete grid graph or discrete graph without considering any uncertainties or robot dynamics. So therefore, the next step I'm going to show you is how we are going to apply this like relatively simple model to real robots by consider the robustness issue, like the robot dynamics issue in the execution part. So the main problem we want to tackle here is how do we handle robot dynamics uncertainty? More specifically, right? So far we talk about a simple robot moving on a vulnerable grid. But in practice, as you can see, the example I show here, right, for different types of robots, they have very different dynamics, and it's non-trivial to use a grid graph algorithm here, right? And also in practice, during execution, there are a lot of uncertainties, either come from the robot itself or because of external disturbance. So we want to apply the algorithms to real robots while handling all these issues. So first of all, the good thing is that the CBS algorithm I just introduced is actually a pretty general framework that can be easily extended to modeling some robot dynamics inside it. So what I showed so far, right, is this CBS search tree. I view it as a high-level planner, right? And there are actually another two components that I didn't talk about in detail. So inside the CBS planner, there's another planner is a single agent path planner. So every time when you generate a new constraint with a new node, you will have to call a single agent path planner to plan paths that avoid the constraint you added there. Right, so there's a single agent path planner. There's also a collision detector. So every time when you find a new path, then you will call a collision detector module to let you know whether the solution is collision free, and if no, then return some collision to me so that I can resolve them in the next step. And so the good thing of the CBS, this framework, is that if you have a particular problem, what you will need to do is to replace the single agent path planner from a grid graph to a domain specific, like a single agent or single robot motion planner or path planner. And then you also replace the collision detector with a domain specific one that can consider, say, robot shapes or even some safety bound you want to introduce to your system. And then the CBS planner itself remains largely unchanged, because if you think about this tree, right, the CBS planner itself is just to, like, the collision detector give you a collision, and the CBS planner will generate some constraints, and then the single agent path planner will give me new paths, and then the CBS planner will rank all those possible solutions and pick the most promising one and resolve collisions there. So the CBS planner remains largely unchanged. And therefore, so in the past, we have deployed this idea into multiple very different like multi-robot systems. Like here is like vehicles at the intersection. These are some drawings go through like windows on the wall. Here are some like robot arms, like where in this case, right, your single agent path planner will be in the configuration space, like the joint angle space of each robot arms. So that's how we are going to handle robot dynamics. But this also has a drawback, because you can imagine if you use a very accurate robot model, then the single path planner can be very, very slow, and we can slow down the entire pipeline. And also, it's okay to model robot dynamics here, but what about uncertainties, right? So even if you plan perfect paths during planning, it's still possible that the robot encounters some uncertainties during execution and cannot follow your planned path perfectly, and then it still collide. So we need something else to handle the uncertainties. And therefore, the second idea here is to introduce an interface between MapPath and control. And then, so what happens is that the planned path from the MapPath set is just like the reference path for the robots to follow. And the actual like robot dynamics or uncertainties all are handled by a local controller or individual robot or individual agent. And so you can view this like planned path as just reference paths, right? But we need to add one more constraint, right? It's not only about reference path, but we also say we want to keep the order in which the agents visit each location. Why this is important? Because if we ignore it, we will see deadlocks and also collisions. So let me give you an example. Here we have two agents. Agent 2 go here, agent 1 go here. So you can imagine that when you plan paths, what happens is that agent 2 will first go to location E, and then agent 1 will go to D, and agent 2 will come back. So that will be the path, right? Agent 1 is just A, B, C, D, A, B, C, D. Agent 2 is B, C, E, C, so B, C, E, C, right? But if you just have this path and let the two agents to use their own controller to execute it, it may have issues, because what if when agent 2 moves to E and agent 1 gets delayed, agent 1 moves too slow, and then when agent 2 follows its path, right, it will come back to location C before agent 1 passes through it. And then there's a deadlock, because agent 2 wants to stay here and agent 1 wants to go to location D, right? So therefore, that's why we want to keep the order. So we will add the blue edges between the same location of different agents, and the edge direction indicates the order, like who should visit the location first. And this is a graph we call the TDG, a temporal plan graph. And with these blue edges, so in practice, what we'll do is that every agent will control its own speed using its own controller. But in the same time, whenever you see a blue edges, you will send a message to the other agent, tell them that, hey, I will visit the location, so now you are free to go there. And then when an agent wants to move to the next location, it will check this graph and say, are those agents who should visit the location already visited the location before me? If yes, then I will go there. If no, then I will wait here until other agent has visited that location. So with this framework, then you can guarantee like it's a distributed execution policy and it's robust in terms of avoiding collisions and avoiding deadlocks. And so moreover, like people in the community have introduced many techniques to further develop like good optimization framework to optimize the specific speed profile of different agents, like if you need different level of dynamics modeling. And so one week we did here is that we discover an issue where if you keep the ordering of all locations, it's really unnecessary. And therefore, we have an improved version in this year's AI where we only add the ordering to critical vertices. So we'll give example about what is critical. So the example here, when we look at the location C, it is critical because if the agents change their ordering here, they will end up with a deadlock. But there are also cases where the ordering is not critical. For example, here, when agent 1 wants to go to here, agent 2 wants to go to here, they both cross location C. But the ordering here is not important, right? Whoever wants to go first, they can go first. And therefore, we will divide the vertices into two types, right? Critical vertices and non-critical vertices. And for non-critical one, we will use bidirectional edges. And with bidirectional edges, then that means the agent can just move in say a first come, first served manner, right? Whoever goes first can go first. And this can significantly reduce the unnecessary weights of the agents. So empirically, we show that at least more than 50% of vertices are actually non-critical. And therefore, by adding these bidirectional edges, we can improve the travel time of the robot by about 8 to 21% during execution. Okay, so that's the execution part. The next one I want to talk about is task planning. So basically, you need to, before you move the agents, you need to first figure out where the goal locations of the agents are. So a traditional or naive pipeline of this framework is that you will have some like independent task planning algorithms, right? And once you plan the path, you assign the tasks to different agents, then you will convert them into starts and goals, and you send starts goals to the task planner, and the task planner will find the path and use the interface that send it to controller. That's a traditional framework. And I would say this framework is great. Actually, it works in many cases. Like the warehouse case is a great decision. But there are also some cases that this method is not ideal. Because first, this is definitely a suboptimal method because when you do task planning, you actually do not consider actual path or the collisions among agents. So it's not optimal. But more importantly, it's incomplete in many cases, meaning that when you assign goal locations to the agents, and later the task planning may tell you that there does not exist any solution that the robots can reach their goal locations without collisions. So this happened to us a lot when we look at like the robot arm case. For example, we use robot arm to do like assembling. Things like the assembled structure are obstacles for the robots. So if you do the task planning first and then later plan paths, it happened to us a lot of times where we cannot find any collision-free paths for the assigned goal locations. And also in many cases, right, the task is not only about reaching particular goal locations. The goal locations always, sometimes often come together with some temporal constraints. For example, in the robot arm case, you may want one robot arm to reach a particular object, hold it, and then another robot arm to perform some, say, attach or detach or some other operations on top of the first robot arm. And in that case, when you reach these goal locations, there's this precedence constraint, right? There's particular ordering of the agents. And that also becomes super hard if you use this decouple method, because when you plan paths, you do not consider, also when you assign tasks, you do not consider paths, and therefore you cannot handle temporal constraints appropriately. So therefore here I am going to introduce like two recent work we have done to combine the target assignment, like how do we find goal locations or targets, with the pathfinding, and in this CBS framework. So the first idea here that we can actually do both target assignment and pathfinding inside CBS together. So traditionally, when we have a CBS tree, right? So every CBS knows what we do is that we plan shortest paths and we detect collisions. If collisions, we branch. That's a traditional CBS. But now, when we have target assignment, that means actually before we plan paths, we need to first figure out what's the goal location of each agent. And to figure out that, so we'll have the first two steps. Well, the first step is to update the assignment cost of assigning a particular goal location to a particular agent. We need to do this update step because when we add new constraints, the cost may change. And once we have the accurate cost, we will run an optimal target assignment algorithm, like Hungarian algorithm, or if you have a more complicated case, maybe it will be a TSP or something else. And after you do the assignment, each agent will know exactly the goal location or the goal sequence to visit, and then you will plan shortcut paths accordingly, and then detect collisions. So with this, we can prove that it's a complete and optimal framework that we can solve the integrated task assignment and pathfinding together. And in terms of temporal constraints, right, it can also embed into the CBS framework. And the idea there is that we want to treat the constraints as conflicts. So here I'll give you one example where we ask agent 1 to reach its goal location before agent 2. So if we treat that conflict, that means at the beginning we plan path, we will ignore this constraint. We just plan short path for the agent. And then, as you can see, agent 2 actually reaches its goal location before agent 1. And then we treat this as a conflict because it violated one of the constraints we have. And when it's a conflict, we will branch and say either agent 2 needs to reach its goal location before or after time 4, or agent 1 has to reach its goal location before time 4. And with this new constraint, we will get a new channel and replan and so on. And then this framework can be embedded together with CBS, right? That means you will have two types of conflicts. One type is this like conflict related to temporal constraints. The other type is a conflict related to robot-robot collisions. And then with one single CBS tree, you can resolve both conflicts together, and then you will be able to find collision-free paths that satisfy the temporal constraints you want. Okay, so that's a task planning side. And then last but not least, I want to introduce some very recent work we have done that look at a different angle of optimizing the entire pipeline for multi-robot coordination. So the motivation is as follows. So far what we do here is that we imagine like when you have a specific application, like for example, in a warehouse, what you will do is that you will first tell me the warehouse layout, like the map, right? And in particular here, let me explain what this map means. So every black cell here represents a shelf that the robot cannot travel through. Every pink cell here is a workstation where there's a human standing there and grab items from the robots. And the blue cells are also empty space, but those are the dedicated locations where the robot will sit there and interact with the shelf, like grab some items from the shelf, for example. And therefore, so the task of the robots is to navigate from a pink cell to a blue cell, to another pink cell, to another blue cell, and so on and so forth, right? So that the robots can either move packages from the shelf to workstations or move packages from the workstations back to the shelf. So that's a tradition, and this is a traditional warehouse layout, right? So what people usually do is that we have the layout design, and then we will fit this layout design into a particular map algorithm, and then we'll try different algorithms or different improvements, so that with the goal that we want to improve the overall performance. And in the warehouse case, it will be the throughput, right? Because agents will get many goal locations, so we care about throughput more often. And in our case, we actually want to do this optimization pipeline in the opposite way. So we say, if we first pick a map algorithm, and then we want to optimize the warehouse layout, can we also speed up the performance? Also, not speed up, like improve the performance, like improve the throughput. And the motivation here is that for this warehouse layout, right, like people use this for decades. And people like it because in the old days, when there are humans navigate inside the warehouse, this very regularized pattern, right, is very friendly to humans because it's very easy for humans to localize themselves. But for robots, why should they care, right? As long as the underlying is a graph, I can perform like search algorithm, dash or A star. There's no difference to me whether the graph has regular patterns or not. So we're thinking like, if we can relax the constraint about the regularized pattern, are we able to find better environment that is more suitable for the robot navigation than humans? So we are targeting some like novel layout that people don't use today. And with the goal that we want to improve the overall throughput of the warehouse. So here's how we are going to do it. we formally model the environment optimization problem as follows. The input or the I would say not input, sorry. The optimization variable is encoded as x, which is just a warehouse layout. So x is a vector of size that is equal to the size of the map. And then every entry of the vector just tell me that particular cell, whether that is a pink, blue, black, or white cell. Right? Then you can encode the layout as a vector. And then you have a simulator where the simulator is already equipped with the particular path finding algorithm, the particular task planning algorithm, and even particular task distribution you are interested in. So everything together in a simulator where we treat it as a black box. And then, so we take the warehouse layout as an input, throw it into the simulator, you will get some throughput. And our environment optimization problem is to improve the throughput. So therefore, we essentially want to solve this arcmax problem, right? Find the best x that maximizes fx. And in particular, in this problem, we are using a type of algorithms called quality diversity algorithms or QD algorithms, where as the name suggests, where we actually care about two things. The first thing is quality, which is the throughput here. We want to find like high quality layouts or high quality maps. But in the meantime, we also care about diversity, which is the preference of the users, and it's user defined like some measurement methods. So for example, maybe you prefer like the layouts to have like more shelves stay together with each other, or maybe you prefer average travel length of the robots, or maybe you prefer to push shelves, I don't know, like more on the like the boundary than in the center, whatever, right? So you can design some functions that can also be measured by the simulator and use them as a preference. And we will give you diverse solutions in terms of this matrix. And so that's the overall like problem formulation. And then here is the algorithm we use. Essentially, this algorithm is a type of evolutionary algorithms, like genetic algorithm style. But it has more components and therefore perform way better than those like very, very traditional genetic algorithms. So essentially what we have is two loops, right? You can see here. The outer loop, what we do is that we have an archive, which is just a set of solutions, a set of like layouts we find. And for each layout we take, we first need to go through a repair step. Why? Because when we generate such layouts using those like random operators, you may generate some invalid layouts. Like for example, the map is disconnected. The blue cells are not next to the black cells, and so on. So we will use a mixed interlinear programming to repair the layout to make a like invalid layout to a valid layout that is as close as possible to the old layout. And once we have a valid layout, we'll throw it into a simulator. And simulator will give us like the score, right? Like the fitness value and the measurements. And then we'll store them into our ground truth archive, right? Which like we just keep the top performing ones there. And then in the meantime, what we do is that when we get these numbers or this data, we'll also use this data to train a surrogate model, which is essentially just a neural network. And the surrogate model is used to replace these two steps because both the MIP and the simulator is time consuming. So we use the data we collect here to train a neural network that predicts the throughput and the measurements given an unrepaired layout. And once we have a good model here, then that's what we have in the inner loop, right? The inner loop performs the normal like random operators on the given map and the new maps. When we have a new map, we'll use the neural network to predict its throughput and the measurements. And therefore, the whole idea here is that we'll perform many, many iterations here. And the archive here will only contain like the solutions that the neural network predicts to be high performing. And then the outer loop, right, is actual simulator and the MIP will only evaluate those layouts that are predict to be high performing. And this overall together can improve our sample efficiency. So here are the results. We pick a scenario with 200 agents, which is a very challenge scenario for human design maps. So for example, here, right? So what we see here is this is the simulation time steps. This is number of finished tasks per time step. It's a very challenging scenario for human design map, and as a result, it's a very bad congestion. and therefore the throughput drops to 0 after like 2,000 simulation steps. But under this map, our optimized map, like the map optimized by our method, actually perform very well. It has very stable throughput like over time. And furthermore, when we take the map here and test it with different number of agents, we can see a big improvement in terms of throughput compared to the human design one. So by now you may be curious, okay, what about how does the optimal map look like, right? So this is a human design layout we use, right, which is the same as the one I showed before. And this is the optimal layout. It looks super random. So then, like, why does it perform well? So we can look at the simulation. Wait. Sorry. Oh yeah, we can look at the simulation. So as you can see, like, there's congestion here and here, right, in the human design layout. But for the optimal layout, no obvious congestion. Everyone moves smoothly. And that actually explains why the optimal layout performs well. But this explanation is also relatively weak because if they are like a warehouse designer, I'm not sure whether I can convince him to use the map on the right because it looks so random and it's very hard for us to understand. So that is actually one drawback, or I would say main drawback of this method. Another main drawback of this method is that it's also very time consuming because we need to encode the entire map as a vector, right? That means when you increase the map size, the vector becomes larger and it becomes harder to optimize. So actually this map size, which is kind of 30 by 30 something, is already almost the largest map we can optimize with this method. And therefore we have a second try. And our idea to overcome the previous two drawbacks is to learn a layout generator. And the key idea here is that if we can have a generator that can capture or discover good local patterns, then first, if you have patterns, then that's easier for human to understand, right? It's more explainable. And second, if you have local patterns, then we can train the layout on small maps and then directly use it to generate large maps by asking it to somehow repeat the pattern it learns, right? And then we can also overcome the scalability issue. So the actual like the layout generator framework we use is this neural network, this framework called NC. So essentially what NC does is that we'll have a neural network here, which is just a CNN, and it will look at a local region, like a 3x3 region of a particular cell, and it will take this as an input, and then the output is an update rule of how you are going to change this particular cell. And this is one iteration. So what we'll do is that we'll apply this neural network, which is kind of an update rule, right, on every single cell on the map, and for many iterations. And people have shown that with this mechanism, the NC is able to generate very complicated patterns in the end by starting with a fixed simple pattern through a fixed number of iterations. And then with this, right, you can easily imagine that the NC is not specific to particular input size. Therefore, it can be used once you have a trained NC, it can be used to generate layouts of arbitrary size. And therefore, so now our problem is not to directly optimize the layout, instead it's to optimize the parameters, right, of this NC network, like the edge weights of the NC network. And how we are going to do that, it's exactly the same story. So we'll use the same pipeline as we use for the direct optimization method. The only change, or the only main change, is that we will change the decision variable from layout to the NC parameters. Everything remains largely the same, although there are some technical detail difference. And with this modification, here are the results. So this is small layouts is the same layouts I showed before. So these two lines are the same, it's the human one and optimized one. But now we have NC here, they are here. So here we have 3 different lines because NC have some hyperparameters, and so we just pick 3 of them here. So overall for these small maps, they are competitive or even sometimes slightly outperforming the optimized layout. But this is actually not where the NC techniques really shines. What it really shows advantage is large layouts. So we train the NC on this small layout and directly use it to generate large layouts. And for these large layers, like this optimized method cannot find solutions at all, while the NCA can still generate very, very good solutions. Like this is up to 1,700 agents, while the human design one is, I don't know, only a few hundred agents. So this addresses the scalability issue. What about like the explainability, like whether it finds good local patterns? And the answer is yes. So these are the two maps or the two layers that the NCA generates for the small and large cases. So as you can see, there's a very clear pattern that the NCA thinks to be good for the simulation setup we used. Although it's not a perfect like pattern because still some neural network thing, but you already see a clear pattern here. And with this clear pattern, then we start to challenge our NCA like pipeline. We say, let's look at a more interesting case. If in the simulation, we change like the frequency of the pink cell, like a workstation, we say, okay, the workstations on the left-hand side are used 5 times more often than those on the right. In this case, what NCA, like what layout the NCA will generate? So it turns out that NCA finds a layout like this. And it makes actually, if you look at it, it makes a lot of sense. Because first of all, it still keeps the old pattern that it thinks to be good, where you put only 1 or 2 black cells together and with 1 or 2 blue cells next to it. It still maintains the old pattern. But in the same time, it puts like more, like less black cells in this triangle area and more black cells in this area. And the reason is that since these pink cells are used more often, there will be more congestion here. So put fewer black cells, like fewer obstacles on the left-hand side will help to relieve the congestion. And so therefore, so I think this NCA generator can be used either to directly generate the layout you want, or it actually is a good tool to give new insights to the human designers about what patterns can potentially be good for your warehouse layouts. Okay, with that, I want to like wrap up of the talk here. So in this talk, we talk about like essentially the 4 components. We start from the method planner, which you solve a simple problem but very scalable, like up to a few thousand agents. We then talk about how to combine it with the execution part to take into account the robot dynamics and uncertainty. We then very briefly introduce like several simple cases about how we can combine some target assignment with the CBS, with the path planner. And last, we give you this like recent work we had on how do we develop a good environment for the warehouse robots. And so before I end, I want to thank all the people who contributed to this work, like my students in the lab, and also many of our collaborators all over the world for contributing to all the work I mentioned today. And I also like to thank you everyone for listening, and I'm happy to take any questions.
Thank you very much, Jiaoyang, for the very great talk. A nice set of works. It's really exciting to see how you're active on all these different threads. Let's open the stage for questions. You can either unmute and ask or write in the chat and I can ask the question for you. Maybe I can be the icebreaker. I have a number of questions, but I want to start with the first one. So I really like the idea of the critical vertices in the first part of the talk. And I was curious about how do you think of extensions of this concept for the cases in which you have uncertainty, right? Here, somehow you are relying on the idea that you know the intentions of the different players, and you can use those to identify the critical vertices. But for certain applications, maybe you have some prior, but you don't necessarily know, right? Can you extend this idea to those cases?
Yeah. So the key idea behind the critical versus is to identify cases where if you swap the ordering of the agents, they are going to have some dead end, like the deadlock, right? So that's the only cases we really want to keep the ordering. For all other cases, like we are okay with first come first go, and so this is like still a very active like direction that we are currently working on. I currently have the feeling that maybe the critical vertices also rely on the structure of the maps, not only on the path of the agents. So I'm currently thinking about the direction that after we have more understanding about like, because the key idea is that how do you know what the vertex is critical or not. Right. So currently our method is that we have the path of all agents, and then we'll perform some graph search algorithm on the temporal plan graph, like the dependency graph we build there, to identify critical vertices. But I have a feeling that once we have a better understanding of them, we can actually match this. We may be able to match these critical vertices and then back to the original graph and say, are those particular locations on the graph, if agent goes through there, we have to enforce some ordering. While for all other empty cells on the map, I don't care it at all. And in that case, then it can be extended to many more scenarios, like the scenario you mentioned, right? Like if we don't explicitly know the intention of the robot, like we don't explicitly know where it wants to go, then that means we all need to set some like traffic rules at the particular, like the gates or narrow entrance to narrow corridors. At those particular locations, you have to follow some specific rules. In all other places, you are free to go. But that's like my ideal case. If we can find some such kind of rules to the original graph, then that will be a nice solution to the cases you mentioned.
Thank you. This makes a lot of sense. Thank you very much. Any other question for Jiaoyang? I hear
hi,
somebody unmuted.
Okay, hi, can you hear me? Yeah.
Okay.
So
yes,
Mael, yes. So I have a question regarding the last part, the redesign of the rows based on cellular automaton principles. My question was, so if I understand correctly, by introducing this cellular automaton, we forced some pattern, the apparition of patterns on regularity, and it outperformed the purely neural network based, which was creating some randomness, which worked better than the human one, but not as pattern based. And so my question was, so because we forced out some patterns which work well, could we extract back, I would say, a regular graph, abstract back the warehouse as a grid and create a graph which is saying that alleyways are a flow graph with the throughput, and say, because we've got patterns, we create a graph with because we've got pattern based, it's very easy to get the throughput, I would say, and abstract back the simulation. I don't know if what I try to explain is
clear. I kind of get the idea. So I guess in our setup, we want the method to be general enough and thus do not rely on specific task planning algorithms. And that's why we do it in a black box way. So that means if you, and that's actually one of the advantages of the framework, because then for a particular planning algorithm you use to clone the agents, you may get a particular map for it, right? So it's like the map optimization step actually make use of some of like the properties or implicit like characteristics of the algorithm you develop there. And therefore, so if you use a flow algorithm to do analysis, I guess then there's a strong assumption that the algorithm are using a particular type of algorithm that can be easily captured by the flow methods. Right. For example, in our case, we are not asking every agent to just follow their short path. In our case, we use one of the algorithms we introduced before, the map algorithm there. So a direct flow that look at the shortest path of the agents may not be informed enough to capture the actual movement of the robots. Does that answer your question?
Yeah, totally. I mean, I agree that the modeling by not going through the flow graph and using the map is what anchors the simulation into reality. No, what I would like to say is these create patterns. So the neural network based create patterns. And because they are so regular, a graph-based representation instead of a map would be quite regular as well. I mean, mappings, and so comparing the previous, the human design one with the newest neural cellular automaton base would say a lot of things about the graph and what flow and throughput we could put on them, I would say. the idea being that is if we want to scale to another problem which is unrelated, saying that we have a nice graph-based description, which is a bit abstracting away the idea of it's a warehouse, and it could be a set of roads in the city or a mapping for a train network or whatever, because we have found out a nice graph structure for that.
Yeah, I got the point.
I mean, it's forward work. It's not.
I got idea. I think, I think it's definitely promising. One thing we might need to think about technically is that currently our entire pipeline, like all the learning model we use there are CNN based. So if we move to graph, we need to find a new structure. But other than that, the overall pipeline should be able to also optimize like any like representation of your solutions. So if we use graph representation, which are more efficient, right? Like given the under the assumption that like either in the warehouse it has this regular pattern that we can easily represent as an abstract graph, or like you mentioned in a city case, right? Then you want the roads and intersections, and therefore graph makes more sense, right?
Thank you for listening to my real
Thank you.
idea.
Thank you, Mael, for the questions. Any other question for Jiaoyang?
I have a question.
Go ahead, Ninja.
Jiaoyang, thanks for the presentation and the talk. And my question is, I'm thinking about a situation that if we fail to track one of the robot or certain number of the robot, and so if such disturbance happens, is there a way to still maintain the performance of the system and to have a certain guarantee for the performance?
That's a good question, and that's also actually a drawback of this current pipeline here, because it's hard for us to provide solution quality guarantee. Like we can still have the guarantee in terms of like completeness, like it's guaranteed to be collision free, dialog free, like agents are guaranteed to reach their goal locations, but in terms of like the travel time, it's unbounded. So that is a limitation of the current framework. When you have that dependency graph, it's hard to predict when one agent delays, how much you are going to delay for other agents.
Yes.
So just add one sentence. So therefore, in practice, what happens is that if the agent delays too much, you may want to go back to the path planning step to replan the path and then go here. So like that is like that execution framework is just like a framework that can handle small delays well, but if there are large delays, it's better to just replan your path, right?
Oh yes. And do you think that like a distributed algorithm would kind of work here? And my question is whether the layout design would change if we use another like strategy to go a bit distributed control.
Yeah, that's a very good question. So we have recently tried a distributed algorithm in our pipeline, like the environment optimization pipeline. It definitely looks different, and the simple reason is that it's not because like it's distributed or not. It's just like because the algorithms are different. So the paths that algorithms are going to select are very different. And therefore, like for example, some algorithm may prefer the agent to go straight forward and give some penalties for turning, while some may not, right? And some agents are more likely to move agents to have more congestion with shorter paths, while some algorithm may prefer to give agents some longer paths with fewer congestion. With all the small differences in terms of preference in the algorithm, it will end up with different environment design. So that's one thing. And then to answer your first question, like for the current pipeline, like the CBS style algorithm, this part is, to me, it's non-trivial to decentralize it. I'm not aware of any good framework to decentralize the CBS algorithm, like the path planning. I mean, there are decentralized algorithms here in this block, but they work very differently. Like for example, one popular way is that you can use like multi-agent RL. That's like a kind of very hot topic to do the path planning here, and then there by design the algorithm is decentralized. But for the search-based algorithm, like I talked with that spectrum, everything there is a centralized planning. I mean, execution is decentralized, but planning and the task planning are both centralized.
Yeah, thanks for the answering.
Thank you.
Thank you very much, Minja, for the question. I think in the interest of time, I want to thank Jiaoyang Li for the great talk. And you see her email there if you want to reach out for more questions. I'm very excited to see where this goes, Jiaoyang. It seems you have many areas that will influence each other soon. So
thank you.
That's very cool. And
thank you everyone.
Thank you also everyone for participating, and see you all next week for the next talk. Bye-bye.
Thank you for the talk.
Bye-bye. Thank you.